Hello, people. What is going on? Sorry, I am late to my own online live recording. This is embarrassing. I have a washcloth this time. That's good. Thanks to my Kickstarter program to get this man a washcloth. How's it going, everybody? Oh, we had one camera on for a second. I saw one of your faces. I'll cherish that moment forever.
I actually left my camera on. I was like, shit.
What's going on?
I'm chilling. What about you?
I'm doing pretty good, man. Doing pretty good. Today, I get to talk about conditional statements with you guys again. We get to argue over if then. It's going to be good. It's going to be good. By the way, I don't know if I said that the first day of class, but if you guys disagree with me, tell me. That's the fun of this logic stuff. Is that sometimes people disagree, and we can talk it through and have interesting little debates, and that's cool, I guess. I mean, I don't know. we'll have respectful debates. We each get time, stuff like that. But anyway, if anyone has any questions, I'm just going to get started. It's 2:34 already. Let's use our time wisely. No questions, no fun stories?
I've been quarantining.
Oh, that's a fun story. You can tell that around the campfire right there. Well, you'd be quarantining, but this will be fun. But anyway, let's get into it then. So we're sharing screen, advanced share, content per second camera. I'm walking you guys through how to do this. Oh no, is it upside down? There we go. I don't understand how to fix this wire. Yeah, I need a USB extender. If anyone knows a guy, they don't want to pay full price. But anyway, so welcome back to Discrete Math, everybody. Last time we ended on talking about if-then statements, and it was very confusing. It's very confusing for a reason, because it's kind of a confusing topic. This one's confusing because like and statements and or statements, like the truth table definition and our intuition matched up perfectly. But here it's not going to quite match up so perfectly, and we're going to talk about it. So first thing I'm going to do is I'm just going to write down the truth table for an if-then statement. And so I called this operation if-then. And it takes in two statements, P and Q. P and Q got to be statements. And then it defines what it does based on this truth table. Where we write P arrow Q to mean P implies Q. And then we have to look at all the options: true, 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 false, false, true, false, false. And the if-then is defined to say if P is Q and true and Q is true, it's like Q followed from P, so it's true. If P is true and Q is false, then it's like Q didn't follow from P, and so we say it's false. But in any case where P is false, we say it's true. And we'll get into why we do all that later and how this actually does make some sense. But anyway, we're just going to have that to compare to things. For right now, let's talk about some of this stuff. Yeah. So let's say first let's just define what we're talking about here. So conditional statements, let's add some color here, jazz it up. Purple. Purple's what we're going with. Do you guys know that purple's not really in the rainbow? Like the rainbow color, like Roy G. Biv. Violet is in the rainbow, but that's because in like Newton, the person that was doing rainbow stuff, back then violet meant more like indigo. Indigo meant more like blue. And then there's like a weird teal thing in between. It was a whole thing. But anyway, purple's a fake color. But conditional statements are any statement with an if-then structure. I.e., I'm probably using commas right, but that's you guys can see the word structure. What do I do to this? There we go. With an if-then structure. That'll work. No, wait a minute. Why am I moving? I'm moving the whiteboard. I should be moving the camera like a smart person would. There we go. There we go. There we go. Yeah. So a statement with an if-then structure, i.e., a statement if P, then Q.
It's starting to unfocus.
Oh, thank you very much. There it goes. I really enjoyed that conversation we had, though. Let's keep up that vocalization here. So where P and Q are statements. And we call P, these colors are random. Let's do pink and, yeah. We call P the hypothesis. And Q,
I want to add on to the conversation, so it's doing it again.
thank you very much. Is it?
Yeah, it's good now.
Nice. See, the camera, it's just like everyone else. I just trouble focusing on math. So P is called the hypothesis and Q is called the conclusion. But it's important to note that these mean kind of very different things from our sciencey way we put like hypothesis and conclusion. Because hypothesis in science is like a claim that you don't know if it's true or false kind of thing. And in this case, we're always going to know if P is true or false because P is a statement. It's either true or false. Like that's the one thing it has to do. But anyway, yeah, so this is what we call the words here. Now, it's important to note also, and we're going to see this. Are you going to focus? You going to focus, buddy? Hey, buddy? Oh, no. You buy a webcam. They say it's 4.5 stars. Maybe it's because...
Is there like a focus lock feature? Yeah, something like that.
Maybe there is. Is it where? Oh, it's just slightly out of focus. Look at that. Anyway, hopefully I'm focused by the time I end this sentence. What I was going to say is that if we say it in the real world, we usually mean cause and effect. Like, for example, I could say that if I write on my face, I'll have a mark on my face. Something like that, right? That's cause and effect. Like the mark of the hypothesis, the writing on my face made a mark on my face. But did I actually make a mark on my face? What would I do for you guys? But the point is, the point is, if then in logic is more like deductions. It doesn't have to be cause and effect. Think about like Sherlock Holmes or something like that. We solving a murder case. Like he'll look at the crime scene and go, okay, if the freaking shoelace of the guy has arsenic on it, then he must have came from this part of England, right? Where in real life, that's not cause and effect. The fact that he had arsenic on his shoelace doesn't mean he's from this part of England. The fact that he's from this part of England means that that's why he has arsenic on his shoecase. But it is true to say if he has arsenic on his shoelace, he'll be from this part of England. You can deduce that. You can deduce the conclusion of my hypothesis. So, hope that makes sense. We'll do some examples of that right now, actually. No waiting at all. Look at this. No delayed gratification. Instant gratification. That's what you guys wanted. So, let's do an example. An example is... if I failed my sensei by quitting karate when I was 4, then I will have felt bad. So notice if then, it also doesn't have to be about things in the future. It can be about things in the past. So I did quit karate when I was 4, and I failed my sensei. He told me not to quit. And so this is going to be our hypothesis P right here. And this is the conclusion Q. And I can tell you, I did quit karate, and I did feel kind of bad about it. My sensei was nice. He didn't interfere with baseball. But the point is, so this is an if-then statement. And based on everything I told you, is this statement true or false? True, right. It is totally, totally true because I did quit karate when I was 4 and I did feel bad about it, right? So that's a totally true thing. Now, what we're gonna do is we're gonna compare our intuition with this statement with, we're gonna compare our intuition of this statement with the actual definition for if then that we just wrote down and I threw somewhere. Where did I put that definition? And in my haste trying to figure out the autofocus, here we go. So let's compare it to this, to the truth table definition. So let's look at P and Q. Let's note that P P implies, I'm not gonna do colors, that's gonna be a whole thing. That P implies Q. That is equivalent to this function if then plugging in P and Q. That's really what it means. And then we know what P and Q are. P and Q are P is true and Q is true. And so, based on the truth table here, if P is Q and true is Q, what's the function output?
True.
True, exactly, right? I mean, that's just following the function. So, our intuitions of the statement would be true, and our truth table definitions of the statement should be true. So it matches up here. Let's do some more examples. So let's say, and notice this is cause and effect. Like the cause of me feel like me feeling bad had the or me quitting karate had the effect that I felt bad about it, right? Now also an example of something that's not necessarily cause effect. For example, if I exist, you might remember this one, then I was born. This is P, which is true. And this is Q, which is also true. I can verify that. I don't need to see a birth certificate. I don't know if there's any Daniel birther movements out there, but the point is, yeah. So this is a statement. And is this statement true or false?
True.
True. Thank you very much. Nice and confident. Yeah, true. Right? If I exist and I was born, I mean, this is really true for anybody, but it's specifically true for me. But notice, and also we can do the same thing with the truth table, where P implies Q is if then PQ, which is again if then true true, which still outputs true. This is pretty analogous to what we just did up there. But the point is, This is not cause and effect. Oh, you guys can see what that says. That says if-then statements don't have to be cause and effect, right? Because me existing did not cause me to be born. In fact, it's the other way around. Me being born is the reason I still exist, right? But me existing means we can deduce I was born. Knowing that P is true is enough to know, knowing P is enough to know Q in this case. Oh, that makes sense. So this is just like Sherlock Holmes deductions right here, right? We're just connecting statements with these logical things like this. So that's totally true. Let's do another example. Let's say if I was tired yesterday, then I must have ran 380 miles in the Moab 380 desert run. Has anyone ever heard of ultra running? It is, you have no idea how amazing ultra running is. They actually run like 300 miles in the desert. It takes them like a couple of days to do it. They, like this one lady, like she's the best ultra runner in the world. And she takes like 1 minute power naps. Like she ran for like 200 miles and then took a power nap for literally a minute, had her trainer wake her up, and then she was like, oh, like totally refreshed after a great night's sleep. Then ran another 100 miles. It's insane. Anyway,
Isn't like the world's longest run also like around a block in like New York or something? Where they just go around that one block like 1,000-something times?
I've heard about that too. People are crazy. I don't get it at all. I get shin splints after running 2 miles. Anyway, the point is this statement true or false? Based on our intuition. I'm honored that you guys are even considering the fact that I must have ran 380 miles yesterday.
It's probably false.
It is false. But am I that much of a mystery, you guys? That's awesome. I did not run 380 miles yesterday. I did run 3 miles. That's not the point, though. This is a false statement. And let's look at the P and the Q here. The P here is true. I was tired yesterday, but it's for a different reason. I was tired because yesterday was also pull-up day. I'm trying to do 1 hour pull-up. It's a whole thing. The point is, I was tired yesterday, but this idea that I ran 380 miles, this is false. So if we look at P implies Q, the if-then, this is going to be if-then PQ, which is if-then true, false. And then if you plug true, false into if-then, what do you get? Point at it. It's false, right? You get false. So once again, though, our intuition for the statement matches up with what the truth table says. So I think you're trying to see why we call this particular operation if-then, because it's lining up with our if-thens. Now, so far we've only dealt, well, we have a few more interesting cases to talk about, but any questions so far? Okay, I guess, hell of a Q&A, but so the point is, I like to think of Q&A as partners, but A is a professional, so there's no Q, the show must go on, so I'm just gonna spit some answers at you.
I do have a quick question, actually.
Yes.
Do we have to be able to know the truth values of our like respective sides of our statements in order to say anything definitively, or is there a way we can like conjecture what we think it might be?
Excellent, 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 excellent question. And this is actually something I was trying to hide because it's a little confusing and it's going to make more sense later. But I'll tell you this. There's a difference between P, single arrow Q, and then we're going to have things later called predicates, predicate, double arrow Q, like that. So P and Q, they're statements. Like remember, we said that like X is even. Is that a statement?
No.
No, because what's X, right?
We don't know. Yeah.
Yeah. So for example, it would not be correct to say X is even. Single arrow implies X is a multiple of 2. The reason being, this is not true because P and Q aren't statements here. And conditional statements specifically have P and Q be statements, right? So that's why we can't do this. However, we're going to talk about a thing called predicates later, and predicates are basically like, they're statements if you specify what X is. So this is a predicate and this is a predicate. So it would be okay to say double arrow. And what the double arrow means is that for any choice of X, the single arrow is true. Like what it means is no matter what X you plug in, no matter what you plug in for X, the single arrow is true. And we're going to go through all that later. But yes, for conditional statements, for just straight up conditional statements with a single arrow like we're doing right now, P and Q are just straight up statements. They can't have any ambiguity or anything you need to plug in or anything like that. However, we do live in the real world, and sometimes people get the single arrow and the double arrow confused, but it's pretty clear in context. Did that answer your question?
I'm good. Yep.
Yes. and I will say, if you were talking about like something that would happen in the future, like if you were to say like if it rains tomorrow, then I won't do a rain dance or whatever. You know what I mean? Like if you did an if this or like that, or like if it's sunny tomorrow, then I'll go to the beach. Well, that depends on it being sunny tomorrow, which you don't know. But I mean, you could think about that as being a statement with a variable of like something it's not a statement because you don't know it yet, kind of thing. Just like X is even is not a statement because it depends on what X is. Is it going to be sunny tomorrow? It's not a statement because it depends on if it's going to be sunny tomorrow. Anyway, yeah. So let's do some more examples. So we could say, excellent. Okay, yeah. So example, if I'll do this quick. If 8 is even, then 8 is a multiple of 2. And I think we can all agree this is true. In our particular case, we have P true and we have Q true. And I'm just going to skip to the punchline. The P implies Q, which is if then PQ is true. And then we also have if 8 is a multiple of 2, then 8 is even. This is also true. 8 being a multiple of 2 is enough to deduce that it's even. So this is true. Don't worry, we're gonna get to the interesting part in a second. That's why I'm going quick here. But for posterity's sake, I'm gonna do all this. Q is true, and then this lines up with P implies Q, which is if then PQ, which is true. Here's the point. Actually, I'm sorry. If P is this statement and Q is this statement, really this here is Q, and really this here is P based on what we defined up here. And so really this statement is Q implies P is what I meant to put. Sorry about that. But yeah, so P is the statement A is even. Q is the statement A is a multiple of 2. It is true that P implies Q. It's also true that Q implies P. If 8 is even, then 8's multiple 2 is true. If 8's multiple 2, then 8 is even is also true. So here's the question. Whenever P implies Q, does Q imply P?
I don't think so.
Why not? That doesn't feel right, does it?
Yeah, because like I feel like there's some case where, like for example, all squares are rectangles, but not all rectangles are squares.
Exactly. Exactly. Something just like that, right, is a perfect example of kind of where this breaks down. It's a fact that all squares are rectangles. So you can say that if something's a square, then it's a rectangle. But you can't go backwards and say if something's a rectangle, then it's a square. It doesn't work that way. So this is not true. But it's not true in general. It's sometimes true, but it won't always work. Like in this case, it's true. If P implies Q and Q implies P, we say, we give a double arrow, meaning they imply each other. And it's called a biconditional. From the Greek bi meaning two, and because I said so, conditional meaning conditional. Yeah. But anyway, this is just a definition to know. So the point is biconditionals are special. You shouldn't expect every conditional to also be a biconditional, if that makes sense. Cool. And we're going to do an example of that right now. All right. So this is going to get weird. Let's say if pigs fly, then I will have a birthday next year. Here's where things get saucy. I say saucy because sauce makes everything better. It's about to get better. If pigs fly, then I want a birthday next year. Is this statement true or false?
I think it's true because you still will have a birthday next year regardless, right?
I still will have a birthday next year regardless. Actually, let's do a few examples at once. If I have a birthday next year, then pigs fly. And then let's also do if pigs fly, then I will respect Justin Fuentes' fourth down decisions. All right. So I'll tell you right off the bat, because it's important for this. I don't respect Justin Fuentes' fourth down decisions, okay? And also, pigs don't fly. But I will have a birthday next year regardless. All right. So here's where it gets interesting. These two bottom statements here. Which one, let's just do this one. Is this one going to be true or false?
False.
False, right? False because if I have a birthday next year, that's not going to make pigs fly. And we can show this lines up with our truth table, and we kind of already did that. We kind of already said, okay, in this case, because we already defined Q is our hypothesis here, but we said Q implies P is equivalent to if then QP, which in this case is if then Q is true, P is false, which outputs, if Q is true and P is false, outputs false, based on definition. So once again, truth table lines up with the definition. So we get false, false. Now, and we can do the same thing, and we can do the same, well actually, we'll do this in a second. This guy right here, true or false? Sid says true. Why say true, Sid? Because P is false. So you're totally right that if you look at the truth table, whenever P is false, P implies Q is going to be considered true. Let's talk about why that is. Like intuitively, if someone told you if pigs fly, then I respect Justice Fuentes' fourth down decisions. Or if it was something like if pigs fly, then I don't know. What else is impossible? Like if pigs fly, then cows fly. If someone said that, would you say that's true or false? And here's where I said we could argue about this because there's no right or wrong answer. What was that? If someone told you if pigs fly, then cows will fly, is that, you think they're telling the truth or they're telling a lie?
I think it's more that they're making a statement that both things are definitely false,
Yeah.
right? Like, and that's why it would evaluate to like, that's why we evaluate it to true, right? Because both things are somehow both like, how to say it, right? Like they're both false, so you basically don't have to regard the validity of like either of them, right? Like it's
Exactly.
always just going to be false.
That's a great way to, that's kind of a great way to put it. You don't have to regard their validity because notice, as soon as you know P is false, you don't have to regard the validity of Q. Q can be true or false, it won't change the answer. Because here's the idea. Here's the idea behind here's the idea of how this makes sense intuitively. And that is, think about if I made a bet with you or something like that. If I said, like, if pigs fly, then and I made a ridiculous bet. Like if pigs fly, then I'll go to the moon. Right? Am I truthful to my bet? In a certain sense, yes, I am. Because did I lie to you? No, because pigs don't fly and I didn't go to the moon. It doesn't matter if I go to the moon or not, because pigs don't fly. The if pigs fly, right? Like this whole statement is conditioned on the fact that pigs fly or not. If pigs don't fly, it doesn't matter what happens, right? Like if I tell you a contingency plan of like, if like North Korea invades, then like if North Korea invades, then I'll hole up in the in freaking war memorial or something like that. You know, like it doesn't matter if like North Korea hasn't invaded, so it doesn't matter. That's a weird. I don't know why I went there. The point is, this is a very weird thing where if P doesn't happen, so you have if P then Q. If P doesn't happen, it doesn't matter what Q is. The statement is going to be considered true. Because we're only saying something about Q in the case if P, right? We're just saying Q will happen if P happens. If P doesn't happen, doesn't matter. So this is called being vacuously true. And let's notice it lines up with our truth table. So here we have this statement. It's the same thing as saying P implies Q, which if we look at the if-then function with P and Q, where in this case, P is false and Q is true, anywhere where P is false, it's going to output true. So this lines up with our intuition. And then maybe I should be connecting these. Yeah. And then same thing here. P implies Q is going to be if then PQ, which in this case is if then false false. But again, as long as P is false, we consider P implies Q to be true, because you kind of can't lie. If P is false, you can't possibly tell a lie. And then this lines up. So this is called being vacuously true. Your statement is true. If your if-then statement's true because your hypothesis is false, that's called being vacuously true, because just kind of say, we're going to consider it true. You could totally make an argument that you should consider it false, but we're going to consider it true. We don't have to consider anything. That's just how the definition works. That's just how this was defined. This is what this operation is. That's how this operation sees the world. It doesn't matter how you see the world or not, just you see the operation, know it's meaning that.
So quick question. If there wasn't a dichotomy and there was a third option of just being like null, would that be like the better option? Or it's true because we inherently decide it to be true, right? Not because of any like logical conclusion.
Yes, exactly. It's true because we decided it to be true, right? Like all of these, like that's why I want to stress the truth table so much, because they're all just defined operations. Like P and true, like P and Q is true in the case where both of them are true, because that's just how it was defined. Like it makes sense with our intuition, but in a weird sense, like how would you define and? Like if you had to talk to an alien and tell them what and meant, you'd probably have to end up making a truth table anyway. You know what I mean? It's kind of more fundamental. But yeah, so that's what that is. What time is it, by the way? I have a clock in here.
3:12.
Oh, perfect. Nice. Oh, we were right on schedule. So, any other questions? But keep in mind, this is kind of interesting, right? This is like deductions and connecting things. This is the first time we're actually connecting two kind of totally separate ideas with what is something more interesting than and or. And we've covered the whole thing. So now we've covered all of our bases. We've covered all of our options. So you can kind of see why we consider this operation to line up with if-then statements that we think about. Cool, cool, cool. Well, anyway, let's do a definition real quick. But keep in mind, this is the great thing about math, right? Like math, you've been lied to your entire life about math. People have always told you in math, like, there's a right answer in the sense that, like, definitively something happens, right? But it really comes all down to how you define things. And so if you want to, you can go back and redefine a different operation where you consider these two to be false, and then you can have a bunch of new different math, and that's fine. It's not necessarily about straight up like this is true, this is false. It's about how you connect the ideas. It's more about this statement being true, and then I can know this statement's true. It's more about, like in the first day of class, we were saying, how can we know things are true? It's more about that dance than the actual answer. But anyway, let's just define vacuously true real quick. Vacuously true. And if then statement, where I'll say, yeah. So otherwise known as a conditional statement, is vacuously true when the hypothesis is false. So that's just what that means. And that makes it really easy, by the way. If you guys are doing a homework problem or something like that, and you have to wonder if the if-then statement is true, if it's a really complicated statement, you can just prove that hypothesis is false, then it doesn't matter. If-then true, vacuously true. Move on. We're saying something ridiculous anyway. Any questions on this? All right. So that is conditional statements. That's the definition. I think that made a lot more sense than yesterday. Sorry for the disaster of yesterday. It wasn't really a disaster. It was downgraded to a tropical storm. But the point is, yeah. So these are if-then statements. Now we can start to play with them, start to do things with them. So let's notice this. If I say P implies Q is true, the only way I'm lying, doesn't matter. The only way I'm lying is if what happens? Because remember,
is it when Q is false or?
so Q is definitely going to be false. However, if P is also false, we consider it to be vacuously true.
Got you.
So you can only lie if P is true and Q is false, right? Like, for example, if I said I was tired yesterday, like if I was tired yesterday, then I ran 380 miles, right? I was tired, but I didn't run 380 miles. So that if then was false because the if happened, but the then did not follow, right? So, No, good. So is if P is true and Q is false, right? If P is true, but Q does not follow. So another way I put this is, if P is true, and Q follows, which is a way of saying Q is also true, or P is just false from the beginning, P implies Q is truthful, right? Because if P is true, then Q follows. If the standard, if P, then Q is totally true. Or if P is false, then we say it's vacuously true. So in either one of these cases, the P implies Q is true. Make sense? Yeah, it makes sense, right? But then think about this. This leads to, what colors are useless? It's important. I'll do red. No, I'll do black. This leads us to a very interesting observation. If P is true and Q is true, or what's a good color? Or P is false, then we say P implies Q is truthful. So it looks like P implies Q is exactly equivalent to P and Q or not P, right? Like P and Q is just saying P is true and Q follows. And then we have or not P is the same thing as saying P is false. Not P true is the same as P being false. So we have this claim right here. This is my claim. That P implies Q is the same thing as P and Q or not P. This expression right here. And how do you prove it?
Truth table.
Truth table, yeah. The truth table crowd has been just waiting all night for this. Yes, P implies true. It was a discrete math class. We were gonna have a truth table. So let's try to prove this. So let's look at P, Q. We're gonna need not P. Actually, yeah, we're gonna need not P. We're gonna need P and Q. We're gonna need P implies Q. And then lastly, we're gonna need P and Q or not P. So in all these cases, these are the four you have to check for a two variable truth table. In the case where P is true and Q is true, well, not P is the opposite, so it's false. P and Q is true because they're both true. P implies Q, by our definition of P implies Q, is going to be true because they're both true. P is true and Q follows. And then P and Q or not P, well, P and Q is true. So it's P and Q or not P is true. One of them is true, so you're fine. In the case where P is true and Q is false, not P is false. P and Q, well, in this case, it's false because they're not both true. P implies Q is false. This is the only way P implies Q is considered false. In the case where P is true and Q is false, because if P happened, but then Q did not happen. And then P and Q or not P, well, they're both false. Not a single one of them are true, so this is false. If we keep going here, here we have P is false and not P is true. P and Q is false because not both of them are true. P is false. P implies Q. That's going to be vacuously true in this case, right? Because P was false and Q was true, which is vacuously true. The hypothesis was false, so we consider it vacuously true. And then P and Q is false. P and Q are not P. Well, it's going to be true because not P is true. One of them is true. And then finally, they're both false. Not P is the opposite, so it's true. P and Q is false because they're both false. P implies Q, vacuously true. If pigs fly, then cows fly. Doesn't matter because pigs aren't going to fly. So we're going to get true. And then, is it true that not P or P and Q is true? Yeah, not P is true. Very true. And then notice these two are identical. Therefore, it is true. I'm not going to write the whole thing, but yeah. So therefore, the truth table shows that P implies Q is just, we can rewrite it like this using ands and ors. And by the way, I don't want this to devalue the idea of if then. Because when I first saw this, I kind of thought like, I kind of thought like, oh, like that, like this is like it's just writing ands and ors and nots in a weird way. I thought if there was a special concept, but in fact, every single binary operation can be rewritten as an expression of ands, ors, and nots. Right? So that doesn't mean if then's not special. If then is still a very special binary operation that lines up with our idea of deductions, which is exactly what math is all about. So we'll get to that. But anyway, this is a true fact that you can use. Now, let's look at this now. We're going to keep this, and then we're going to ask, oh, green. I'm going green. What is the opposite of P implies Q? Put a different way, what's the negation of P implies Q? Because P implies Q is the opposite. Or the negation is the same thing as just saying take the opposite. So, yeah. So if it's opposite day, for example, right? If it's opposite day and I say P is true, that means P is false. If it's opposite day and I say P and Q is true, that means that P is false or Q is false, because that's the negation, right? On opposite day, what's it mean if I say P implies Q? This is a good question, right? This is a weird one. On opposite day, if I say if P, then Q, what do I really mean? Let's look at the truth table here, right? So on opposite day, if I say P implies Q is true, it means that P implies Q must be false, right? That's what opposite day is all about. Best day of the year. So it should be a national holiday. So if I say P implies Q is true on opposite day, that means P implies Q is false. And the only way that can happen is if P is true and Q is false. So another way to put this, the opposite of P implies Q being true is P implies Q being false, which must mean P is true and Q is false. So I hope that makes sense, by the way, right? Because because the only way you can lie with an if-then statement is by saying P is true and Q is false. So let's prove it. Claim the opposite of P implies Q, the negation of P implies Q equals P and not Q, right? Because we said that's the only way we can lie with if-then statements. So, how can we do this?
Truth
Truth table.
Truth table. I like your instinct. We can totally do that. I'm gonna go a little off the wall here, right? I want to be unpredictable, and I'm gonna actually prove this using our laws, right? Because this.
De Morgan.
And so we could do it using our laws. So, I'll do this. I'll say proof. Not P and Q. So like this is the claim, and now we're doing the proof. Not P and Q. That's the same thing as not P and Q or not P by the above. Which you prove with a truth table. And you can just use that as a fact. Then, what can we do here? We kind of have two options.
You could maybe expand out the knots of P and Q using De Morgan's law?
Yeah, I think it's a good idea. I think we should distribute this knot using De Morgan's law. And so this is going to become not P and Q, flip that or to an and, not P, by De Morgan's law. Then this is going to be equivalent to, well, we can take this not P to P by double negative law. Then, this right here, yeah. So now what should we do from here, you think?
Another De Morgan?
De Morgan part 2.
De Morgan part 2, exactly.
A reckoning.
My precious battery. It's dying. I knew this day would come. There we go. Cool. So, exactly, De Morgan's law part 2. Revenge of De Morgan. Yeah. So then we can do De Morgan's law here to treat that negative to get not P, flip that and to an or, not Q, and P by De Morgan's law. All right. We still have a little more to go, though. What can we do next? Because we haven't gotten to this statement yet. I think we're kind of circling in on it. We haven't gotten to it yet.
Can we distribute the, actually, never mind. Ignore it.
I know, that was a good word, distribute, right? This is exactly the distributive law. We have a statement or another statement, all parentheses, and another statement, right? So we can distribute this and. Maybe the first thing we should do is rewrite it like this. Maybe that might look better. And we could do that by the commutative law. Uh-oh. Oh no. so like commutative law, we can do that, and then this is exactly the distributive law. The distributive law says we can distribute this P and. This is going to P and not P, or P and not Q by distributive law. And now I'm going to pick this up here because I ran out of space. So then this is equivalent to, well, what's P and not P?
Always
Just
false.
returns false.
Always returns false. That's a tautology, right? It always returns false. So we get false or P and not Q. Yeah. Because P and not P always equals false. We're going over that. Now, here's the last interesting step. What's this equivalent to?
You could take out the false or, because if P and not Q is true, it doesn't matter anyway.
Exactly. I didn't write this down in this version of, like, in this, like, kind of shrunken version of the laws, but we had this, we went over all the laws. I think this was the absorption law or the idempotent law. The point is, this is going to be P and not Q, because notice if P and not Q is true, we're going to have false or true, so it's going to be true. If P and not Q is false, we're going to have false or false, which is false. So this statement is going to be the same thing as whatever this statement is. They're going to line up. You can prove it with the truth table. And this is by, I want to say absorption.
Could that be an identity law?
What?
Could that be an identity law?
This right here?
Yeah.
This is an identity law.
It is? Okay.
Yeah, and I'm pretty sure it's called the absorption law. Yeah, we went over that 2 classes ago. But yeah, what time is it? I feel like it's probably time to go, isn't it? 3:33, perfect. The point is, though, we started with not P implies Q, and we got down to P and not Q. Meaning, what? This is equivalent to this, equivalent to this, equivalent to this, equivalent to this, equivalent to it goes here. But the transitive property, this is equivalent to this. This claim is true. So this is the negation. This is the negation of a conditional statement. And right before we leave, I'm just gonna say one last thing, and that is it surprising that this is the negation? Would anyone have intuitively thought it would look different? We have a bunch of very intuitive people here. That's nice. So a lot of people think that not P imply or the negation of P implies not P of P implies Q is going to be Q implies P. Not true. Some people think that the negation of P implies Q is going to be not P implies not Q. Also not true. A lot of people think the negation of P implies Q is not Q implies not P. Not true, and this one's actually especially not true. They're always going to be opposites. But anyway, yes. The negation of P implies Q is not another conditional statement. That's all you need to know. These are not true. Do not make these mistakes. I think there's like 75 of you in this class, and statistically speaking, historically, 45 of you are at some point going to make one of these mistakes. Don't do it. You can beat the odds. Okay, look me in the eyes. At least one of them. I can't see my face. The point is, which I can't see my face, which I'm complaining about. I feel like I have the right to see my face, but in a regular lecture, I can't see my face anyway. So this is just like normal. But anyway, the point is, the opposite of P implies Q, the negation of a conditional is not another conditional statement. It's just this. And this cannot be written as a conditional. It just isn't one of these things. Right? There's no law of the universe that says that the opposite of a conditional has to be a conditional. And in fact, there's a law of the universe saying it's not. So this is the negation. If ever you're asked what's the negation of a conditional, this is it right here. It's not one of these. This is called the inverse, this is called the converse, and this is called the contrapositive. And we're going to go over these next time, but neither the converse, inverse, or contrapositive are the same thing as the negation. Negation is totally separate. And that's the end of class. Any questions?
Can I quote you on in a regular lecture, I can't see my face?
Absolutely.
Cool.
Yes. That's 100% true. That's a Daniel Valvo guarantee. I haven't taught, actually, okay, I did teach in one room with a mirror, but I specifically didn't look at it because it's not about me, it's about you guys. Okay, well, that's class. Let's stop recording. Ugh. Off.